The experiments we are going to do in this film have to do with the superhydrophobic effect. Suppose that you had some sort of complicated fluid flow over a surface, and suppose it were possible, by magic, to make that fluid move upon that surface as if there were zero friction. Although no such surface in actuality exists, we can approximate this effect with a phenomenon known as the superhydrophobic effect. The hydrophobic effect is the tendency of a substance to repel water. Let's remember that the contact angle is the angle conventionally measured through the liquid where a liquid interface meets a solid surface. Superhydrophobic surfaces are highly hydrophobic. In other words, they are extremely difficult to wet. In this case, the contact angles of a water droplet exceed 150 degrees. Now let's investigate how water droplets behave when falling on a traditional surface versus a hydrophobic surface. As seen in this clip, when water falls on a plain surface, the fluid spreads and sticks to the surface. This is called wetting and is a common phenomenon we observe every day. When water falls on a superhydrophobic surface, its molecules are repelled from the surface. This causes the droplet to come back together, bounce, and roll on the surface. Let's examine how water acts on hydrophobic surfaces in different situations. Here is water being sprayed into a funnel coated with a hydrophobic spray. Notice that the water, rather than wetting and draining into the center, rolls quickly across the surface, maintaining its speed and momentum as it circles around the funnel. Here, the water is being sprayed onto a curved piece of paper coated with the same hydrophobic coating as the funnel. Notice how the droplets roll up and down on the curved paper like tiny marbles in a bowl. Now let's discuss how hydrophobic surfaces work. Superhydrophobic surfaces are created by taking an already hydrophobic material, such as Teflon, and implementing a microstructure that creates air pockets between the surface and the fluid. The superhydrophobic effect can be seen with this strainer coated with a hydrophobic material. The air gaps between the fluid and the surface prevent wetting, allowing the water to be held in the strainer due to surface tension, rather than falling through the mesh. When pressure is applied behind this mesh, the hydrophobic coating cuts the water flowing through into many smaller streams. When this same experiment is performed with a traditional strainer, the fluid sticks together and flows as one stream through the mesh. This strainer has a tighter woven mesh than the one before. When the mesh surface is hydrophobic, the stream is broken into many fine streams. Again, when the fluid flows through the uncoated mesh, it flows back together into one stream. The potential uses for superhydrophobic materials are unlimited. Research in this area is ongoing, and we encourage you to learn more about it on your own. Thank you for joining us.